Okie dokie. So we've talked about circles, and now we're going to talk about ellipses. So to do that, let's take a look at the domain and range of this thing. So I'm going to take a look first at the domain. So here's my domain. Let's think about this equation before we even jump into that. Let's take a look at this equation. So we have 9x squared plus 25y squared equals 225. Notice here, no matter what x and y you plug in, x squared is going to be positive, and so is y squared. And so this is always positive, positive, that equals positive. Now, if this means that x and y actually can't just be anything. So we already know that the domain and range are not all real numbers. And here's how I can tell. So if I'm looking at the domain, I have 9x squared would equal 225 minus 25y squared. Oops, sorry about that. I'll divide both sides by 9, and we'll get x squared equals 225 minus 25 y squared over 9. And then I'm going to take the square root of that. So x is equal to the square root, and notice since I'm looking at x squared, I would want the positive square root and also the negative square root, because those would both be okay, of 225 minus 25y squared over 9. I can actually simplify this a little bit because I can take the square root of the 1/9, so that would just be plus or minus 1/3 the square root of this thing, 225 minus 25y. So let's think about this. Inside the square root we need a positive number, or at least a non-negative number. And so I want 225 minus 25y to be greater than 0, or greater than or equal to 0. Now notice here, I said I was looking at the domain, but I'm actually looking at the range here. Because look, what y values are going to make this okay? So that's kind of funky, so think about it. But right now I'm going to find the range. And we would do the opposite, or the, how should I say, the opposite. We'll look at the y values, solve for y to essentially find the domain. So if I solve this inequality, this would be y squared. That's important. So y squared. So if I solve this, I'll get 225 greater than or equal to 25 y squared. I can actually divide both sides by 25 here. So I'll do that. And I'll end up with 9, but greater than or equal to y squared. Okay, this is where we want to be careful, and I mentioned this before in the circle example, where if I take the square root of both sides of an inequality, it doesn't work out just the way you think it would with an equation. So if I take the square root of both sides, that would leave you with 3 is less than or equal to y. But that's not the entire solution set, because I could plug in y equals -10 for this, and that would be totally true for 3 is less than or greater than or equal to y, excuse me. If I plug it in for this, that's obviously not true, because that would say that 9 is greater than or equal to 100, which is not true. So this is slightly more complicated. Let's think about this. What are the numbers that when you square them are equal to 9? Will that be plus and minus 3? If you take any number between plus and minus 3 and square it, well, it's going to turn it positive, but it's also going to be less than 9. For example, plus or minus 2, when you square that, you're going to get 4. Plus or minus 1 squared would be 1. And so actually, the way you want to look at this, another way to look at this is saying that y, or the absolute value of y, is less than or equal to the square root of 9. Essentially saying that, sorry, I'm running out a little bit out of space here. 3 greater than or equal to y greater than or equal to -3. And so this is actually the range of our equation. Okay, so if I do a similar thing, and I'm going to kind of keep this side by side. So that was actually to find the range, which is right here. If I work this the opposite or kind of parallel case, I'll get, let's see, I'm going to start with 25y squared equals 225 minus 9x squared. I'll divide both sides by 25 like I did before, except I divide by 9. So I'll get y squared equals 225 minus 9x squared over 25. And I'll take the square root of both sides. Now, this is just like before, I could take the square root of 9 out. I'm going to take out the square root of 25. Just makes the algebra a little bit easier. So I'll have y equals plus or minus 1/5 the square root of 225 minus 9x squared now. And so similarly, to find our domain, I need that 225 minus 9x squared to be at least 0. And so now, if I'll go about and kind of fast forward this step, but this will leave us with 25 is greater than x squared, which means that x has to be between plus or minus 5. And that would be our range, or sorry, our domain. So now that we know our domain and that we kind of know what what an ellipse looks like, we can kind of just draw the graph from here. Here's our graph. So our y values are between plus or minus 3, 3, negative 3, and 5 for our x's. Plus or minus 5, about there and about there. If I draw a little box here, then this tells us where our ellipse is contained. And we've done this before when we talked about just domain and range of functions in general, or relations in general. What the domain and range, what you do is essentially you put a box around the function, or the relation, excuse me. And so this ellipse is going to look something like this. Okay. So I want to, oops, sorry about that. So I want to take another dive into how the pieces of the equation relate to the features on the graph. So I'm going to copy this equation right here. So we had 9x squared plus 25y squared equals 225. And what I'm going to do is divide everything by 225. So I'll divide that by 225, 225, 225. Now, just first off, you can kind of see where the features are, because 9 is 3 squared, and hey, from the center, which we can see the center as being in the origin in this case, because this was a very simple case. Hey, that 3 ended up right there, and the 5, which is right here, 5 squared is 25, we can see it right there. But let's look at this. If I divide everything by 225, what happens is that, well, let's see, 9 over 225 is actually 1 over 25. It works out nicely in this case because, again, this was a planned example. Plus y squared over 9 equals 1. This equals 1 is going to help us get it in a sense of standard form of an ellipse. So when we have our conic sections and they equal 1, it actually lets you know, and then you could, again, rearrange the left side nicely. It lets you know pretty quickly what the graph is going to look like. The way I'm going to rewrite this in a little bit more, or rearrange it, is to factor it essentially. So instead of x squared over 25, I'm going to have x over 5 squared plus y over 3 squared equals 1. The reason this is nice now is because if we look back at the original, the distance from the center vertically or in the y direction was 3. And that's where we can see the 3 here now. And similarly, the x distance from the center was 5. And that's where we can see the 5 underneath the x. We're going to call these things the quote-unquote x radius and y radius. We're still using the term radius because ellipses are not super different than circles. And so, in general, the equation of an ellipse is x minus h over, we're going to call it rx, r sub x for the x radius, squared, plus y minus k over r y squared equals 1, where, again, rx or ry equal the x or y radius. And by the radius, what I mean is from the center straight out to in the x direction, how far till you reach what we can think of as one of the vertices, I guess, of the ellipse. And likewise for the y direction. That's what we mean by radius. And also, HK is also the center. So I didn't use that, or I didn't make an interesting center in this example just because it's our first example. But you can imagine that if we had centered it somewhere else, just like a circle, the center is going to be at x minus the x coordinate and then y minus the y coordinate. I mentioned before that that ellipses and circles are very, very similar. And what I mean by that is that actually you can think of the ellipse as the parent of the circle. The reason being is because if x and y are the same, sorry, not x and y, but the x and y radii are the same, then you actually do have a circle. So for example, let's actually just take a look at one that's very similar to the one we just worked, which would be, oops, sorry, there was some scratch work over there. Let's go down here. 9x squared plus 9y squared equals 225. And so what I can do is if I divide everything by 225, because I want it to equal 1, remember, to make it easy for me to identify, divide everything by 225, well, this is going to be x squared over 25 plus y squared over 25. It's just equal to 1. And so I can see here that I'll have x over 5 squared plus y over 5 squared equals 1. Oops, 1. And so my ellipse is here centered at the origin, and I go out in the x direction 5, out in the y direction 5. In other words, you're just going to have this. Where this is 5, this is negative 5, this is negative 5, and that's 5. If that wasn't enough to convince you, you might think of it like this. Instead of dividing by 225, if you had instead divided by 9, so I'm running a little bit out of room here. If I divide everything by 9, you'll get x squared plus y squared is equal to 25. And that is probably the more obvious statement, or obvious evidence that it is a circle. I want to wrap this video up with just a little bit of vocabulary. So I'm going to come back to our example that we drew. So there's the center. The center is the center as you would expect. What we call the long axes, we'll say. So this is essentially the direction of you would essentially figure this out by which radius is bigger, the x radius or the y radius. But the larger of them tells you where where the minor axis and the major axis is. So in this case, our major axis is along the x direction because our x radius is larger. And so I would say that my major axis, is equal to 10. Major axis being the length of it from one pole to the other pole. So that's, well, we'll say the length of the major axis. Length of the major axis is 10. And likewise, the length of the minor axis, because it's shorter, is equal to 6. For some reason, we need to always add in like kind of extra layers. So if I just wanted like this half, we would also say that that is the length of the, not the major axis, because that would be the whole thing, but the semi-major axis. Sorry, I shouldn't have put that here because it's squished, but in this case, the semi-major axis is 5. And the semi-minor, the length of the semi-minor axis is 3 in this case. There is one more important thing, but that deserves its own video. And so we're in a later one, we're going to talk about that. But in the next video, we are going to do one example of given an equation, find the graph of the ellipse. And that example is right here.